Hello, everyone. Uh, I am Gaurav Vikhe from Acceleration Robotics, and thank you all for attending ROSCON India. I think it's going to be a tough act to follow Angelo after that really killing interactive session, but I'll try my best to keep you guys awake. So, primarily, what I'll be talking about today is ROS-based hardware acceleration for industrial productivity. Now, before we get into that, I'll first like to address what hardware acceleration implies. If all the people who know what hardware acceleration means, could you just raise your hands? Except people who've already met me at the stall. But apart from that, okay, that's good enough for me to get into definitions. So primarily what we mean by hardware acceleration is that currently robots that are deployed, they have to sense, then decide and act in real time. And that requires a lot of computational capacity. Now, for that, if you stick to a standard CPU-based architecture, it won't suffice, which is why a lot of us try to go for other compute substrates where we find that, okay, if you offload it to that compute substrate, whether it be a GPU or an FPGA, you will get better performance. Now, how do you define better performance? Primarily for a roboticist and even for end customers, industries where robots are deployed, they care about three primary factors. One is latency, that you want the robot to have minimum latency. It needs to act and it needs to decide and act in real time. So low latency is a must. You need to have high throughput. You would want your robot to deliver sensor-rich information in real time as quickly as possible. So that is something that is another facet of hardware acceleration. And the third thing is power. What I mean by power over here is that you essentially reduce the number of times your robot has to recharge. For example, everybody's probably seen Peppermint's robot, right? You would want the robot ideally to, let's say, have a lesser time spent at the docking station and more time spent cleaning. So that's how we look at hardware acceleration, and these are the three primary parameters that we try to optimize for. So let's take a very simple example here. Yeah, so this is a standard perception example of a Harris detector. And if you just run the Harris detector on a CPU, whereas if you deploy a hardware accelerated option, whether it be a GPU or an FPGA, in this particular case it is an FPGA, you see speedups of up to 30x. Now that is something that allows you to take on more the robot can take on more responsibilities in real time. It can give you, it allows you for a better inspection, a better perception approach. So now we'll get into uh, what we did as an open source initiative a year back. So hardware acceleration requires a special set of skills, right? Now you can't really solve for that. You can't really optimize that experience. It's something that you have to just, get your hands dirty and learn. But what you can solve for is essentially making an interface that allows you to standardize how hardware acceleration approaches are deployed. And that is what Acceleration Robotics tried to do with the Hardware Acceleration Working Group. And the main result of that was REP 2008. REP stands for ROS Enhancement Proposal. What we did achieve in the REP 2008 was try to standardize the approach in which hardware acceleration solutions can be deployed into the ROS ecosystem. So we provided standardized APIs, we provided guidelines as to how you should be writing a hardware accelerated package. So let's say someone's written a accelerated point cloud filtering package on a GPU, then it should be fairly easy for any other company or any other hobbyist to try it on their own GPU, whether it be of a different make or whatnot. So that's what we achieved to do with the Hardware Acceleration Working Group. The REP 2008 is officially accepted into the ROS guidelines. And now, with all of this, I would get to the case studies. So one thing that we realized as we worked in Acceleration Robotics is that we have put up, we've engaged with the ROS community, but the one thing that was missing was actually getting industries to understand what this implies for them, which is where the motivation to pursue case studies, to actually reach out to the end customer and ask that, okay, what exactly do you want to be faster or have higher throughput or have battery efficiency on? And that is what resulted into two case studies that I'll be talking about, which are the meat of this talk right now. So the first one that we did was accelerating metal parts manufacturing. So over here, we worked with this company in Spain called the Selsa Group. And primarily, as the name suggests, they are a metal parts manufacturer. This is what their setup looks like. So this primarily is a perception problem. So I would like you to observe how the part after being picked up is being aligned with the other metal parts on the screen. Oh, it's not playing, sorry. Yeah. Oh, no, wait. Anyway, I'll just move on. I'm not sure why the video wasn't playing before, but essentially what we did here, I'll skip to the next step. We created a digital twin of their setup, and the digital twin was used firstly to analyze, okay, where exactly do bottlenecks in their perception pipelines lie. So just for context, the video was 13 seconds long because that's how long the cycle time was for the part to be once it is picked up, to be aligned with the other metal parts on the assembly line. So what Acceleration Robotics did was create a digital twin to firstly analyze, to firstly trace through where are the, let's say, possibilities for parallelization in their current software stack. And this is what the digital twin looks like. So obviously, as I mean, the graphical detail will suggest it was using NVIDIA ISAC sim. And post that, what we did achieve for them was we used our own IP core known as robot core perception, which allowed us, you'll see a difference between how it was being detected earlier and what we have achieved to do. So we not only did we accelerate the pipeline, but we also got them more precise results, which is what the video on the left shows. So now what does this look like in actual numbers? What is the hardware acceleration pipeline leading to? How does it help the final the end user? Is you will see on in the digital recreation what the 1x reproduction of this hardware accelerated pipeline looks like. There's a clear-cut difference, and from a numbers point of view, we managed to achieve a 62x hardware accelerated solution for them. So earlier they were taking 13 seconds, and right now they are taking 200 milliseconds to align that metal part to the assembly line. So that's the first result. We think of this as a pretty significant result. It has led to increased productivity in their assembly line currently. And now I'll be moving on to the next case study, which is here, what we are working with is Technia. Technia is an automotive parts manufacturer based in Spain. And their primary issue was that they were using a Fanuc robotic arm. And as some of you may be aware, the legacy robot manipulators have certain sort of speed controls embedded into the robot. So what they wanted from us was they wanted an operational acceleration, that they can't really move forward with speed, but can something be done to analyze their stack such that we can make it faster in some other way and reduce their cycle time. So again, we followed the same approach where we again created a digital twin for their current setup. And the one thing that I forgot to mention was that what do we use essentially to, let's say, understand where computational parallelization can be done. And that's through standard tools like ROS2 tracing, if they are in the ROS2 ecosystem, or LTT-NG. These two tools are open source, and they have helped us achieve the kind of results that I am showing you. So the first thing was the digital twin and then the tracing. Post that, what ended up happening was we basically found places in the trajectories that they were following where there was no need to increase speed as such, but you could still get a 16% increase in the robot movement. Now, the problem with this approach was we were still breaking a few constraints that Fanuc had laid down. So this was not of business interest to Technia because, I mean, they need service from Fanuc, so they couldn't really move forward with it. So they came to us with, okay, how do we solve it in another way? Now, the result of that was what we did, as the slide title suggests, we figured that probably adding another robot into the mix would be a way to go forward. And for that, what we first did was we modeled mathematically where do overlap times lie? Where does let's say adding another robot into the mix lead to let's say minimization of time from transfer of part one to, let's say, another machine. So we looked at that, and this is the mathematical model of it. The slides will be available, so you can take a deeper look at it at that time. But what that led to was so with dual manipulation, obviously, the mathematical model did suggest to us that yes, we can get a lower cycle time. But that also came with another responsibility, which was that if you add another robotic arm into the mix, then how do you optimize the assembly line itself? Where do things get placed? Which is where, for us as a hardware acceleration company, digital twins are tremendously useful. So we made the setup for them, and what it resulted into was a 10.78% faster robot movement. Now, 10.78% may not seem like a huge number, but when you're operating at a scale of an industrial manufacturer, what it looked, the cycle time was reduced from 13 seconds to 11.5 seconds. The Gantt chart shows that, it's completely spaced very tightly. The earlier Gantt chart was, there were a lot of blank spaces in the middle because they couldn't really, the movement wasn't optimal. So what that looks like from a numbers point of view, what it looks like is, obviously we did increase their decrease the cycle time to by 11%. But from an end user's perspective, is, let's say, because we are asking a tremendously huge ask, which was that add another robotic arm into the mix. But when you get results like this, when you can add 800 units per day, which translates to 20K units per month, then the business is happy to put in more money into it. And this extends to every other sort of, robotic subtask that we may do, whether it's navigation, whether it's localization. If it's coming at an additional cost, which is, let's say, which is undermined by the ROI that you're getting, then companies are more than happy to implement such solutions. So that's what we ended up achieving with this, and I'm open to questions.
Any question?
Hi.
Yeah.
Great talk, very insightful. I just have one question. Like, creating a digital twin seems very painful. Like, how do you go about it? Like, what procedure say do you follow?
It is painful. I won't deny that. It's just that something you have to be patient with it about, because, like, as a consulting business, we have to do that. We have to figure out a way where we don't have to be present at the client's location, and we are free to do experiments which we won't be able to do with actual hardware. So that's something that, we've sort of learned to just accept that it's something that you have to do. Tools like NVIDIA, Isaacsim, and Gazebo do help out. We've used both of them for certain situations where, let's say, photorealism is not really important or is not a main priority. We go with Gazebo. Where photorealism is important, we try and stick with Isaacsim.
Thank you.
Okay, thank you, Gaurav, for the talk.